Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized by IST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
Okay, good afternoon. My name is Michał Piłaci, and I will be the host for today. The theme of this week is machine learning and engineering design. It is my great pleasure to introduce our motivational speaker for today, Dr. Faez Achmed. Faez is an assistant professor in the Department of Mechanical Engineering at the Massachusetts Institute of Technology, MIT, where he leads the Design, Computation, and Digital Engineering Lab. His research focuses on developing new machine learning and optimization methods to study complex engineering design problems. Before joining MIT, Faez was a postdoctoral fellow at Northwestern University and completed his PhD in mechanical engineering at the University of Maryland. He also worked on the railway and mining industry in Australia, where he pioneered data-driven predictive maintenance and renewable planning efforts. And today, his talk will be about design synthesis from the lens of machine learning. And Faez, the floor is yours.
Great. Thanks for the introduction, and let me share my screen. Great. So hi, everyone, and thanks for the invitation for this talk. I'll talk about design synthesis from the lens of machine learning. Just quick intro about myself. I lead the Design, Computation, and Digital Engineering Lab at MIT in Mechanical Engineering, where we work at the intersection of human-driven design as well as physical sciences-driven design, where on one side you have things like how do you model customers and how do you understand teams. On other side, you have simulations, optimization, generative design, and so on. Today, I'll talk about design synthesis. And the key motivation for our talk is how can machines design machines? So this is a bicycle. This is a bamboo bicycle, which was created by an inventor, Craig Calfee, where he came up with this unique idea of how do we create designs which are meant for people based in sub-Saharan Africa. Now, the question is that we have these designs, and most of these designs are generated by human experts. But what we start thinking about is how can machines create these complex designs, and what are the key problems in achieving a future where machines can work together with humans on creating better and faster designs. And for this idea of creating designs, we broadly think about design synthesis or creating new designs. And there are 3 main categories. So there is rule-based design, data-driven design, and topology optimization. I'll mostly focus on data-driven design. Again, there is this whole idea of generative topology optimization and rule-based, which we'll not touch today. And talking about designs, again, for folks who are more on the computational side, that's quite evident. But for a person who is in a bike shop, they have to think of how do you even represent a design in a computational format. And the 2 major ways to think about is that you can either use traditional parametric representation. So you take a bicycle, for instance, and you can measure everything and put it in a big vector and represent it as a parametric design. Or you can think more on the machine learning based compact representations, which is a lot of what the modern deep learning does is how can you learn these latent space embeddings, where we assume that the manifold hypothesis is true, that most designs lie on a low dimensional manifold. And why do we want to do this? Because once we can learn any low dimensional representation of these designs, so once we can take a physical object and put it in a vector format, then we can start doing things like creating new designs. We can think about performance prediction, optimization, finding the design which is, say, highest performance or exploration and recommendations. So giving recommendations to new people, to new designs when a person goes to a bike shop, for instance, like what design suits them the most. And again, this is not a completely new idea. There are a few directions of research where design synthesis has been quite effective. For instance, it has been used to generate aesthetic car images. It has been used for aircraft models where you can create entire CAD models. Or Hyundai has been working with some researchers in Korea on generating wheel designs and how do you generate diverse set of wheel designs. Our own work has shown like more on the metamaterial side, how can you think about unit cells and how do you assemble them together to create more complex designs. However, when we look at all these research work, there are certain unique challenges which we find, which off-the-shelf models cannot handle. And today, I'll touch a bit on those unique challenges and then wrap up with what are the open questions which are still out there. And to look at these unique challenges, we will look at the example of synthesizing aerodynamic shapes. So this is a typical example of an airfoil. If you cut the wing into half, you see this cross-section. And again, these airfoils are used in turbines, propellers, bicycles, cars, and so on, where you want a certain shape and you want certain performance. One typical performance is, say, lift to drag ratio for aircraft. So you want maximum lift and you want minimum drag for an airfoil, right? And before like thinking about what we can do with machine learning, we have to think of what have people been doing since they have been designing aircrafts. And they generally, the process is an optimization-based process where you represent an airfoil, say, using points on the surface. You parameterize it, then you change those variables using some rules, evaluate it into a physics-based solver, and then make those changes again and again. Now, again, this process has been effective, but it suffers from the problem of it's iterative and slow. And also, it does not transfer knowledge. So if you have designed 100 aircrafts, each new airfoil starts from scratch. On the other side of things, we have these generative adversarial networks within machine learning. And a lot of us know about these deep fake human faces, which where they have been used to create human faces, which are quite realistic to existing faces. Now, one may just think like, why don't we take generative adversarial networks and apply it to designs? So we'll take a lot of airfoils, we'll look at them and generate very realistic looking designs. And that solves our problem, right? That's design synthesis, that if it works so well for human faces, it will work for designs. Well, that doesn't happen in practice, because when you start thinking about designs, you have to think of performance. Unlike human faces, each design has certain performance associated with it, which comes from some physics solver. Then second and third thing which we care about is diversity. So if all airfoils look the same, then that's not good for us. So we care a lot about coming up with designs which are different from each other. And related to diversity is the idea of novelty, that we learn from a data set, and by design, generative adversarial networks want to create a design which is similar to the data set. But can we come up with this one design which is unique and we have never seen before, or it's outside the box? And again, these are some unique challenges of engineering design, which you think about when creating new designs. They apply to any domain, whether you are creating an airfoil or a bicycle or a car. And one example where we tried to address these challenges was around this model called PAT-GAN, which is Performance Augmented Diverse GAN. So you take an existing GAN model and you integrate something called a determinantal point processes, which is a probabilistic model for modeling diversity, as well as integrate it with physics solvers, which can give you performance. And what we found was that when we come up with this new architecture specific for design problems, again, I'll not go into the details, you can refer to the publications for these. We get some quite interesting results. So on the left-hand side, you are seeing all the designs which are generated, again, a two-dimensional embedding of those by a typical GAN. And you can see it pretty much mimics the green dots, which is the training data. But when we start thinking about maximizing diversity and quality, we see that it can generate things which are outside the box and were still very high quality. The quality is shown by darker colors. So the quality kind of pushes the envelope towards high quality regions. And then diversity makes it go into the areas where it can benefit in quality itself. And the same results are shown for all the typical metrics we care about. The same ideas can be extended to multiple objectives. So now you can think of, instead of one performance, when you're designing any design, you have multiple performance metrics, then you can take ideas from multi-objective optimization literature to enhance your GAN models. And further, so one idea of GAN models is that they can generate samples which are high quality, but then you can also think of downstream optimization in the latent space. For instance, in this case, we looked at latent space of Bayesian optimization, where you can use these design parameters with the learned space, and you can optimize it using a high fidelity performance estimator, and you get quite good results with the Pareto front. And just to give you an estimate, what we are looking at here is the performance of these models. On the x-axis, we want to get higher faster. So this is a FFD, which is typically used in for airfoils, free-form deformation method. You have SVD method, which gives much better performance than FFD if we want to find these Pareto optimal front for airfoils. When you use a typical GAN, just take an off-the-shelf GAN and apply it, what we see is that it pretty much performs close to one of the traditional optimization methods. However, when you start thinking about these custom designed GAN models, what we see is that they can lead to more than 186% performance improvements. And not only that, they can lead us to designs which were not in the training data set. And that is what leads them to these big improvements in design. Great. So again, we talked about performance, but then when you're creating new designs, you also think a lot about constraints. So for instance, this is an inverse design problem where what we want is to create airfoils which have a specific performance. So that's more like a constraint, that I want a design which meets exactly 0.65 value of performance. And you can think about how do you achieve this in a continuous conditioning case? And this is much tougher than typical conditional generative adversarial network because of data sparsity issues, as well as thinking about what do you even mean as an exact performance? Is 0.64 good enough or not? And we can think of new architectures, new loss functions, which can give you these designs for every given target performance. And not only just airfoils, when you extend these models to more complex designs, so these are aircraft CAD models, for instance, and thinking about different types of constraints. So let's say I want CAD models which have width with aspect ratio between 0.1 and 0.3 and volume between this and performance between this and this. So you can define multiple range constraints and start thinking about how can we use new types of generative adversarial network which can follow these real world constraints. And when we start thinking about these problems, we are still scratching the surface, because although these constraints are giving some interesting results, a lot of real world constraints are still very subjective. So people are like, I don't like this constraint. And how do you even model them within a machine learning framework is an open challenge. Some of the other open challenges which I've highlighted here are data sparsity. So here what you can see is that almost all of the data is in a very small region of the training data is in a small region of the performance space. And what that means is that when I want to design an aircraft, for instance, with 0.8 and 0.8, there is no data which the model has seen. And how do you enable it to create designs even in those cases, as well as thinking about uniformity and quality metrics. So these are, again, some open challenges which people have to think of, like these complex simulations and multiple objectives and so on. But the key message which I wanted to highlight was thinking about design requirements. And when we are creating these machine learning driven design synthesis, how do you model design requirements, which is an open challenge. And again, the applications are not just airfoils. You can think of designing UAVs, cars, bicycles, or even this is an example on the right-hand side, you see the ventilator design, which MIT Mechanical Engineering created for the pandemic. And how can we enable machines to create such complex designs with multiple moving parts, which work in the real world and which can be generated quickly as well as can be manufactured. So I talked more on the simulation side. I would also like to highlight the human side of things. So, and this, I would like to show the example of bicycle design problem, where you have, you want to generate new bicycle designs, which obviously meet your performance simulations, that they should have low lift to drag ratio, structural performance, and so on. But they also meet customer preference, which is a question which my group is looking at right now. So for just like most other data-driven methods, you start with some data set. In this case, we created a data set in collaboration with the BIKECAD software company, which is specific CAD models for bikes. And you can start analyzing the design space of these bikes. Like what do you even mean by a road bike? What are the MTBs and trials and children bikes and so on, and how they are situated with respect to each other. And then we can use some of the generative adversarial networks model, mostly focusing on the image in this specific case, to create these new designs. So you see these designs are created by GAN models, and they are quite realistic with parts which are with focus on even small parts. And again, there's a lot of details on how you can achieve this. For example, you have to think of individual parts and how can you augment the model to create focus on even small parts and so on. The details are mostly in relevant citations, which I have noted. Great, so we can create designs, but then also there comes the idea of human preference. And this is something which we are looking at right now, thinking of how can you ask people what they like, as well as you can take these measurements of people. So by just looking at these measurements of people, we can pretty much predict their aerodynamic performance. But now also thinking about how can we learn their preferences and then create design which meet those preferences from the latent space. Another open question, thinking about design synthesis, is about creativity. And creativity is a tough challenge for machine learning because, first of all, humans don't agree on what creativity means. Like there is less consensus, and consensus also depends on the design domain. So for instance, this is one specific model where we showed that machine learning models can identify unique designs and then copy those signatures of those unique designs to create more designs which are considered creative, using a combination of novelty detection, segmentation, generative adversarial network-based rewriting, and so on. So yeah, I mean, at the end, the key message is that generative models, when they are designed properly, can enable us to synthesize complex designs. And this is a growing area. So if you are interested in research, I would be happy to chat. And there's a lot of challenges which are still open, where we have to think of what happens in real world designs when we have less data, when we have multi-physics simulations working in the domain, as well as domain knowledge and so on. So these are, again, thinking about interpretability, creativity, and how do we make designs which are similar to what humans would generate. With that, I would like to thank you all. And at the end, our goal is to create a world where humans and AI can design together to solve our biggest challenges. Thank you.
Thank you very much for the inspiring talk. And I would like to remind the audience to post their questions in the chat for a joint Q&A at the end of the session. And today, our deep dive speaker is Mina Konakovic. Mina is a Schmidt Science postdoctoral fellow at MIT Computer Science and Artificial Intelligence Lab, mentored by Professor Wojciech Matusik. She earned her PhD in 2019 in the School of Computers and Communication Sciences at the Swiss Federal Institute of Technology Lausanne, EPFL, advised by Professor Mark Pauli. She received her master and bachelor from the University of Belgrade, Faculty of Mathematics. Her research focuses on computer graphics, computational fabrication, 3D geometry processing, and machine learning, including architectural geometry and the design of programmable materials. She received an ACM SIGGRAPH Outstanding Doctoral Dissertation Honorable Mention, the Geographics PhD Award, and was recently awarded the 2021 SIAM Activity Group on Geometry Design Early Career Prize. She will give us a deeper view on transforming design and fabrication with computational discovery. And Mina, the floor is yours.
Thanks for the kind introduction. And it's my pleasure to be here today. Let me quickly share my screen. And please give me a heads up, Michal, if something cannot be seen. Okay, so today I'll talk about some of my previous work that I did during my PhD and my postdoc. And let me immediately dive into the talk. So I will discuss how computational methods are transforming what and how we can design and fabricate. Design is everywhere. It's in everything we need to create. It's behind the creation of buildings, engines, machines, and products. In chemistry, we need to design chemical ingredients, new molecules, and drugs, and maybe even vaccines nowadays. And in computer science, we design abstract forms, for example, neural network architectures, data structures, programming languages. Even writing a program is a design process. However, the problem with all these designs is that they are still mostly manually created. Now, what do I mean by manually? We start by designing an object, sketching it or recording it in some form. Then we have to build it in real or virtual world. And only after that, we can test and retrieve the performance of the designed object. And if we're not satisfied with what we obtained, we need to go back to the beginning, adjust the design, and iterate until we're happy with the result. So we can end up doing a lot of trial and error before we get the final design. And the problem with this is that it's slow, it uses excessive resources, and often requires expert knowledge and intuition of how things will work. And in today's talk, I will discuss how we can transform this with computational design. We already saw how forward design works. We design an object and then we can check the performance. And the performance we can look for is, for example, whether the shape is right, whether the dynamics are good, or maybe how good is the mechanical performance of the object. And for example, we can design a structure of a robot and only then test how fast it can climb the stairs. And this is the forward design. It's mostly considered manual. But wouldn't it be better if we could take the performance requirements as our input and get the optimal design parameters generated automatically? And that's exactly what the inverse design is for. Obviously, this needs to be done with algorithms. And that's what my work is about. I believe that computer science and mathematical models are essential for transforming the design practices and improving what and how we can fabricate. And throughout this talk, I will show 3 different projects that solve 3 different inverse design problems by using or developing completely different algorithms, techniques, or theory. And we will see solutions with new geometry processing algorithms, deep learning approaches, and data-efficient machine learning. And all of these methods were developed for the purpose of solving design and fabrication challenges, but with potential impact to more general problems. And although these problems all seem completely different and maybe in a few different domains, they follow the same solution strategy. And this will become obvious until the end of the talk, where I will also give a summary of what we did. And just a quick spoiler alert here, I will spend more time discussing the first project than I will spend on the other 2. And now let's dive straight into the first project, design of auxetic structures. First of all, what are auxetic materials? They are engineered materials that have this unintuitive behavior. When the material is stretched in one direction, it also expands in all other directions. And they appear in many different forms, like this 3-dimensional foam or a triangular linkage. They are also used in automotive industry for electronically actuated devices, art, fashion, and so on. But the problem with all these examples we've seen before is that they're all limited to very simple geometries. They're either planar, spherical, or cylindrical, but not more than that. And our question in this project was, can we approximate more complex surfaces with auxetic sheets? So can we create an inverse design algorithm that will find the right configuration of the material to achieve the given shape? And to answer this question, we start by looking into how to create an auxetic sheet. If we take a sheet of flexible but inextensible material like this thin acrylic here, it can bend freely, but it cannot approximate even a simple shape such as a sphere because there is no stretching in the material. But if we insert a regular pattern of slits into the very same material, it turns an inextensible material into a uniform auxetic. And now it can stretch, it can wrap around the sphere and approximate a larger class of shapes. But the problem now is that if we take a piece of this material and just try to wrap it around the complex target surface, in most cases we will fail. And that is because of the global coupling happening in the linkage. If you stretch the material on one side, it is unclear how it will affect the other side of the material and how to even align it with the features of a given surface. So we had to look into material deformation more closely. And first, we have abstracted the pattern in the form of a kinematic linkage composed of equilateral triangles. And what we noticed is that the material scales approximately isotropically. Now, this observation provides a direct link to conformal geometry. And just to give you a brief overview of what the conformal geometry is, it is a transformation that allows local rotation and uniform scaling, but not shearing. And in other words, conformal mapping preserves angles, but not lengths. And we can characterize a conformal map with a local scaling factor. And in this transformation example on the right, you can see that the mapped squares preserve the 90-degree angles, only the edge lengths can vary in scale. And again, we want to do things that are curved, that have curvature more interesting than just zero. And here the Gaussian curvature quantifies how the surface is bending locally. If it is zero, it means that it is not bending at least along one direction of the surface, like the cylindrical example. If we have bending in two different directions, the curvature is negative. And if it's bending in the two same directions, then the curvature is positive. Now, our goal is to establish a relationship between the local stretching of the material and the curvature of the surface we need to approximate. And for this, we can use the Yamabe equation that relates the local change in Gaussian curvature and the variation in conformal scale factor. And this essentially tells us how much variation in stretching we need to introduce into the material in order to achieve a certain curvature locally. And while this equation has been studied for a long time in mathematics, what people did not study so much is the fact that in our physical material, the scaling factor is also bounded. We cannot stretch the material arbitrarily. And once the material is fully stretched, it expands 4 times in area or 2 times in length. In other words, this limits our scaling factor to be bounded between 1 and 2. Now, what does this mean in practice? If we take any simply connected domain, for example, this face of Max Planck, Riemannian's theorem guarantees the existence of a conformal map to the plane. But this theorem assumes that we can have unlimited scaling. And in fact, in this particular example, the scale factor is 59 because the curvature, the change of the curvature is huge around the nose. And this is much larger than our admissible range for the material that we have at hand. So to solve that problem, we have to use some things that are a little more technical, but basically the idea is to introduce the so-called cone singularities. And effectively, what that means is that we cut the surface open. We are going to push some of the curvature into the boundary and release some distortion by creating more boundary that the surface can float into. And in this example, just a single cone singularity reduces the scaling factor to be below 2. And this opening here the opening angle is not random. It is prescribed to match the kind of cutouts we can have in the triangular linkage we are working with. And this is fundamental because otherwise we could not realize the surface with physical requirements we have. Now, our final algorithm looks as follows. We start by finding the locations of these cone singularities and compute the conformal map. Then we overlay a grid of regular triangles over this 2D domain to determine the 2D layout of the material and the local stretching we need in 3D. We then run a 3D optimization to lay out our auxetic linkage onto the target surface. And effectively, what we are doing here is we are running a global optimization which pushes the linkage close to the reference surface and makes sure that the triangles remain rigid and avoid collision. And we can nicely formulate all these geometric constraints in the form of distances between the vertices of the triangles and use a nonlinear solver to obtain the final solution. And because the problem is nonlinear, it is important to note that the initialization with conformal map is essential. Otherwise, we could get stuck in local minima. So this is how the final approximation looks like. And you can see that it opens up and closes at various amounts across the surface, depending on the curvature in each region. And to verify our approach, we fabricated the mask example with the copper sheet. And here is the final result. So thanks to our global optimization approach, we are able to obtain the approximation without visible seams. And the triangles along the cut match up perfectly. So from the tip of the nose to the bottom of the chin, the triangles are preserving the topology and their connectivity everywhere. And another example is this high heel shoe made from aluminum auxetic sheet. And again, it is really non-intuitive that you need a 2D layout like this to approximate a target shape. And here is the video footage of the fabricated prototype. So this is not a rendering, it's an actual artifact. And again, you cannot detect the seam where the 2D patch is connected together to form a closed loop. And lately, these materials and patterns started popping up everywhere. We see them in architectural structures, in sports shoes, sport clothing, wearables, even in personalized orthopedic casts. And I'm very excited to see what other applications will enable in the future. And another thing I haven't emphasized so far is that this material can be used to generate transformative structures. With the same piece of auxetic material, we can approximate different geometries, like these two different faces. And while this can be beneficial for some applications, it also makes the fabrication tedious because we have to achieve the exact openings computed by the algorithm in each region of the material. And this inspired our next research question. And the question is, can we program the 2D material to be able to approximate exactly one 3D shape once deployed? And that's exactly what we did. We designed programmable auxetics. In comparison to uniform auxetics that have identical triangles and variable openings in the surface, the programmable auxetics are fully opened everywhere, but vary the scale of the triangles. And this way, we can take the material and simply stretch it out everywhere to achieve the encoded shape. And in the programmable auxetics, we encode the maximal local stretching that the material can have. In the region with the smaller and already open triangles, there cannot be more stretching, while the central region with larger triangles that are in the closed configuration here, the linkage can stretch out of the plane quite a bit. And again, to determine the local stretching that we need depending on the surface, we can use the Yamabe equation and the conformal mapping. And in this case, the optimization pipeline is a little different than before. And I'm happy to discuss the details offline, but in the interest of time, I will move on to tell you a little bit about the deployment mechanism we used, or how we transform the material from the flat state to the target 3D shape. What we observed is that both inflation and gravity can work as mechanisms that can stretch the material. But not any shape can be made with these mechanisms. And that's where the interesting geometry comes in. Namely, if we think of inflation as a volume maximizing action, and we look at the example of a ball with an inward bump, if we continue to pump the air inside of this ball, the bump is simply going to pop out. And because we are filling more air volume inside and there is nothing to keep the bump in to prevent it to go out. We observe that this phenomena can nicely be captured with a differential geometry concept of mean curvature. Mean curvature measures the divergence in the unit surface normals. So inside of the inward bump, the normals are pointing towards each other and resulting in a negative divergence. While on the outward bump, the normals are pointing away from each other and having the positive divergence everywhere. And inspired by this observation, we were able to introduce and prove a new theorem that essentially says, if you have a surface of a limited area and a maximized enclosed volume, the surface has to have positive mean curvature everywhere. Now, this is great because it can immediately inform our algorithm what kind of shapes we can hope to achieve. So if the user provides a target shape that is physically unrealizable, we can automatically detect the problematic region and edit it towards the closest realizable shape. So no need for the user to manually go back and forth with the design until she finds the version of the shape that can actually be inflated. Okay, now let's see this in action. For a target shape like this one, we compute the optimized programmable auxetic linkage in both 3D and 2D. And the linkage is then laser cut and lifted with a generic rubber balloon, and it stops the inflation when it reaches the prescribed shape, once it's fully stretched everywhere. And we can also use this technology to make a Mars habitat. Because the Mars pressure is 10 times lower than the pressure on Earth, the habitat needs to be pressurized anyway. And we can conveniently pack the flat sheet of our material in a box, ship it to Mars, and simply inflate it on site without any additional construction material or scaffolds. And another interesting application may be found in heart stents that are inserted in the heart to unclog a blood vessel. And typically, these are made regular and straight cylinders, but however, a study from 2016 argues that this is problematic for patients with clogged vessels that are curved. They propose how to make a curved balloon that expands the stent, but they do not have a solution for the metal part that stays in the vessel. And with our method, we can now scan the patient's heart, detect the clogged vessel, reconstruct the 3D model, and design a stent optimized exactly for that patient's needs. I also mentioned gravity as a deployment mechanism, so I'll briefly show an example of that. And again, we can only do surfaces of positive mean curvature, but can allow for unintuitive negative Gaussian curvature like the saddle point in the middle. We take the programmable linkage and just need to hang it, and it will go to a prescribed shape. And you can see that thanks to our optimization approach, we are able to create a linkage that can keep this unintuitive saddle point in the middle part of the linkage. And of course, it's always nice to see your research used in actual products. A gravity-deployed shading pavilion designed with our technology will soon be built on EPFL campus, next to the famous Rolex Learning Center. And to recap our key contributions in this project, we show how conformal mapping is crucial for understanding and modeling complex auxetic surfaces. And now we can approximate any input shape. And then we introduce a new class of auxetic materials called programmable auxetics that have a unique 3D shape encoded in the 2D material. And finally, we prove what kind of surfaces can be realized with inflation if the surface has a limited area. Okay, back to the talk outline. So far we've seen design of physical structures. Now let's move on to the next level of complexity, where we design dynamic structures where we optimize both the body and the brain of a robot automatically. So we have a physical structure and the brain that controls how it is going to move in space. And today, most of the robots are designed manually for a target purpose. Many of us have seen videos of robots that are designed for specific terrains, whether it's a flat ground, natural environment, or climbing buildings. And in each case, we can see that the structure of a robot defines which tasks it can perform. And this design direction is manual. Now, looking in the opposite direction, automatic robot design requires solving an inverse problem where we go from a set of desired capabilities to a robot structure. And our recent work presents a workflow for automatic design of co-optimized robots and controllers for a given terrain. Everything is automatically done, no need for human input. And while we are proposing a solution for terrain-optimized robots, this can be easily generalized to other robot design problems. And the workflow starts with the user providing a set of input components and a desired terrain that the robot should be able to traverse. And terrains can be challenging, non-repetitive, and asymmetric, like unevenly stepped terrain, wall obstacles, varying size gaps, ridges, and so on. And regarding the input components, the user provides the set of links, joints, and end structures, and their properties she wishes to use for the robot assembly. Now, if we would manually try to check all possible configurations and keep in mind that the configurations may easily include 50 or 100 different components, this could take a lifetime. Now, not to mention that many of these configurations would not be fabricable or able to walk. So what should we do about this? How can we automate the design process and which arrangements should be allowed? And to answer these questions, we use grammars. We borrow this theory from natural language processing community, and more specifically, we work with graph grammars. So first of all, we abstract the structure of a robot in the form of a graph, where each node represents a robot part, such as body links and joints, and limb components. And to enforce the symmetry in pairs of limbs, we simply copy one limb branch to the other side of the body. And this directed graph can then easily be turned into a kinematic tree for simulation. And what is a graph grammar? It consists of a set of symbols and a set of derivation rules. And these symbols represent abstract concepts such as robot head, robot tail, and a grammar always contains of a start symbol from which the derivation needs to begin. And each rule has a left-hand side and a right-hand side. And applying a rule to a graph means replacing an instance on the left-hand side in that graph with the right-hand side of the rule. So to generate a robot design from the grammar, we start from an initial graph consisting of just the start symbol. We then apply a sequence of rules by replacing the nodes appearing on the left-hand side of the rule with the nodes on the right-hand side of the rule. And here's how we can create a simple example. We begin from a start symbol. We then apply a sequence of rules that keep on adding more and more robot parts until we reach stopping criteria. And finally, our complete bio-inspired grammar looks like this. We have structural rules that form the body structure and the part-based rules that select the components. And this slide is cluttered, but the message that I want to convey here is that all the rules that we need to generate hundreds of thousands of different robot designs can fit into a single slide. And more importantly, the generated designs are all inspired by animals, are all fabricable and able to walk. And here we can see some example structures that our grammar can create, but these are still not optimized for a given set of terrains. we need an algorithm solution, an algorithm that will identify the best ones. And the brute force approach here would simply take too long. And what do I mean by not optimized? This little fellow, for example, with extra long limbs is not the most optimal for crossing the ridges. And the one with wheels have the added mechanism for climbing, but would be much better going downhill than climbing stairs. And we obviously need a way of finding more optimal designs. So we develop a deep learning-based approach that learns heuristics in simulation to not simulate and test hundreds of thousands of different designs, but to quickly discover structures that work best for a given terrain. First of all, to learn the controllers and be able to simulate the robot, we use a popular approach called model predictive control. And since this part is not our major contribution, in the interest of time, I will skip the detailed explanation. I just wanted to mention that we compute the performance of each robot with the reward function that makes sure that the robot is facing forward, staying upright, and walking as fast as possible. And our strategy for identifying the best solution works as follows. We can think of the design space defined by the grammar as a search tree, where the start symbol is at the root of this tree, and each branch generates a robot by following the sequence of rules that are stored in the edges of this tree. And once we have a complete robot design, we can simulate it and compute its performance. Now, in this example, we would be looking for the branch on the left, as it has the highest performance value. But deriving every single branch all the way to the end and simulating every robot for hundreds of thousands of different designs is intractable. And we need a way to estimate some values for incomplete designs represented with dashed nodes to determine early on which branches are promising. But we cannot really simulate partial designs of the robots because we can only simply simulate the robots and compute its performance when we have the whole structure. And we want to be able to predict if what is the best performance going to be lower in each branch. So to come up with a prediction scheme, we developed a method called graph heuristic search. Our method is inspired by reinforcement learning and the well-known A-star search, but instead of manually designing the heuristics, we learn the heuristics with a graph neural network. We learn an approximation of the reward function V by using the simulated values of several designs to train a graph neural network. And after training the GNN model, we can use it to predict the maximal rewards for each branch early on and see which are the promising branches to explore further and which to immediately abandon. And after training the heuristics function, the process repeats for a fixed number of iterations and gradually converges to an optimal design. And here are some results. This robot uses its highly articulated front limbs and a front body joint that allows for lifting the front body part to clear the ridges. And the optimized robots in here can rapidly change directions by swinging its head and pivoting around its front legs to efficiently avoid a series of walls. And this completely unintuitive structure proves to be better performing than all other designs. An unevenly stepped terrain is one of the more challenging terrains for robot simulation, and the optimized robot has these front hooks for climbing and simple back legs to save energy. And to recap our key contributions in this project, we introduced a system for co-optimization of robot structure and brain for a given terrain. And we showed how to automate the robot design with graph grammars. And we developed a new algorithm to efficiently search a combinatorial design space for best performing designs. And more importantly, this same strategy can now be used to design other types of task optimized robots. So far, we've seen projects where we could use computational methods to compute the performance. And in the last project, I want to show you what happens when this is not possible, when we have to get physical artifacts and test them to obtain their performance. And in this case, we work with severely limited number of data points. And the whole idea started in the project for autonomous discovery of optimal material formulations. We had a set of chemical ingredients that we could mix in a different ratio to get a new material formulation. And we then needed to fabricate the material samples with, for example, 3D printing, and extract the mechanical performance of the material with compression testing. And because the mixing, the fabrication, and the testing process are very slow, we could only process 4 samples per day. And we were looking for some way of cleverly selecting which samples to test in order to discover the best performing formulations. And for this, we needed an optimization algorithm to guide the whole development. So the general setup for our algorithm is the following. We have a d-dimensional design space and an m-dimensional performance space. And design space may refer to, for example, percentages of each of formulations we mix. And the performance space is, for example, how elastic the material is or how much energy it takes to break it. And because the material is, we have multiple objectives that we want to solve for, we needed to solve a multi-objective optimization problem. And in multi-objective optimization, objectives are often conflicting, leading to a set of optimal solutions with different trade-offs rather than a single optimal design. And we call these designs Pareto set and its image in the performance space Pareto front. And the goal is to find Pareto optimal designs while the algorithm has to take care of 2 key challenges. The first challenge is that the objectives are black box functions. So the mapping between the design and the performance space is unknown. But we can retrieve the values at certain locations by fabricating and testing samples. And the second challenge that we have is that the testing is time and resource expensive. So the number of experiments and data points is severely limited, and not like in many other machine learning applications where you have thousands of training samples at hand. Here, this means that we have to choose wisely which samples to evaluate in each iteration. And a problem setup like this can be found in many applications in, for example, molecule and drug design, in engineering design, material science, developing trading strategies, optimizing robot controllers, tuning hyperparameters for neural networks, and so on. So how to solve this problem? And the answer can be found in multi-objective Bayesian optimization. We developed an algorithm that uses a standard Bayesian optimization pipeline, but with several improvements to the components. First, we fit the Gaussian process on the set of input observations for each objective independently. We then extract the approximations of the objectives by simply taking the means of the fitted Gaussian processes. We search for the Pareto set and front of these objectives, objective approximation functions. And from that Pareto front, we select a batch of points to evaluate next. And we iterate through all the steps until some stopping criteria is met. And the first 2 steps are commonly used in other Bayesian optimization methods. Our main contribution lies in the last 2 steps of the pipeline. While other methods typically obtain a discrete and sparse approximation of the Pareto front, we use the so-called KKT conditions that once we find a single point on the Pareto front, they let us quickly discover large and continuous regions of Pareto optimal solutions around them and the corresponding Pareto set. And then a key insight for our selection strategy is that these solutions are often grouped in disconnected regions spread across the space. So we define a diversity metric to encourage sampling from various regions of the space while also trying to maximize the hypervolume improvement. And the hypervolume improvement is just a standard quality measure of the obtained Pareto front. But in contrast to previous works, our diversity metrics takes the knowledge from both the design and the performance space to better select the batch of next experiments. And just to illustrate the advantage of our solver and selection strategy, here we show a performance-based comparison of a standard test function against other popular and state-of-the-art methods. And our approach, shown on the bottom right here, reaches the ground truth Pareto front much faster than other algorithms without getting stuck in local minima. And we performed extensive evaluations on synthetic test functions and monitor the hypervolume improvement. And our algorithm, shown in purple, consistently outperforms all other relevant methods. And because we worked with Fabrication, we also ran tests on the real-world data sets. And again, our method achieves better results. And currently, the process of optimal experiment design is still mostly done by hand and based on intuition. And because we developed an algorithm with state-of-the-art performance that can be used by researchers and engineers in many different disciplines, we decided to develop an open source platform that is easy to use for users with zero or little experience with optimization and machine learning. And it has a built-in visualization and a distributed version for teams of workers that can operate in parallel, even from remote locations, which is particularly convenient in these pandemic times. And now a scientist or a technician can see the values proposed by the algorithm to test next, go ahead, evaluate them, and simply enter the obtained performance back into the system. Or the whole process can also be completely automated, where the platform would be integrated as the brain of the system that automatically generates and tests samples that are requested. And this work is currently in submission to Journal of Machine Learning Research, but we already started collaborating on projects for 3D printing material design, acoustic filters, battery design, and robot optimization. And we hope that our work will help bridge the interdisciplinary gap and find applications in many more problems. And finally, to recap our key contributions in this project, we show a data-efficient method with the state-of-the-art performance for automatically guiding the optimal experiment design. And the core advantage in our optimization method lies in the multi-objective optimization solver and the selection strategy we developed. And we are very excited about our open source and easy to use platform that should help applications in many different disciplines. So we saw how different algorithms and techniques can be used to solve inverse design problems. And I hope I made a point that with computation, design and fabrication can solve much bigger problems and become much better. And none of these solutions would be possible without algorithms. And to find inspiration for new algorithms and applications in need, I believe that the promising and important research questions can be found in deformable structures, such as the telescopes or solar arrays, in soft robots or mechanisms that have deformable bodies, but also some kind of a brain, and in 4D printing, which is essentially 3D printing with the fourth dimension being time, and personalized medical devices. And advances in computational design and fabrication will enable us to successfully do patient-specific implants, prosthetics, and ultimately organ printing. And some examples like this are already designed manually, but my question is, how can we automate the design process here to accelerate the discovery of better performing solutions? And also, can we create inverse design tools that will find optimized designs that are customized for a specific user or a specific environment? And I'm very much looking forward to see how we're going to answer these questions in the future. Finally, I want to mention that none of this work would be possible without the support from great people. Huge thank you to all my collaborators, mentors, lab mates, and fellows, and of course, the schools and funding agencies. And now I guess we can open it up for questions.
Thank you very much, Mina, for the great talk. And we still have some time for a short Q&A. And the first question is for Faez. So how is the design for the bicycle gun parameterized? Does it work in the image space?
Yes. So right now it is in image space, and we have also worked on parametric space and CAD models, but the results I showed were image based. We have separate models just for parametric, as well as some work on 3D CAD models.
Then I have a question for Mina. Can we increase the scale factor for the auxetic structures beyond 2 by recursively cutting the pattern, such that when we have some challenging region, when we have to stretch it more, we could have some finer triangles inside, which would then allow for this stretching?
Yeah, there are these so-called hierarchical auxetic patterns, which let you have other types of other numbers for the scaling limits. And yeah, those are definitely interesting to explore. So the scale factor of 2 is just for a triangular linkage. If you had other patterns, it would be a different number.
And do you think they would allow to break the limitation of 0 mean curvature, or would they still be limited by that?
Yeah, you mean the negative mean curvature. No, that limitation is not related to the auxetic pattern. It's simply related to the deployment mechanism, which is inflation, and the limited area that you can cover with your material. So it doesn't matter that you're working with auxetic material. It's simply that you're trying to maximize the volume inside of the surface, and the surface that you're approximating has a limited area that it can cover.
Thank you very much. So another question for Faez. When you are using a gun, they are on the inside working in a latent space. So they're observing data and building up a latent space of the variables. And in many of the designs, for example, for the wings, there is some sort of implicit latent space that humans are using for developing in them. For the wing, it could be some sort of set of Bezier curves. So do you think that constraining the gun and giving it some hint of the design space could boost the exploration? Because if it is observing only a limited set of designs, then as a result, the parameterization inside of the gun would also be limited to those designs.
Yeah, so that's a good question, and that's exactly what we do. So for example, for the airfoils, we use something called a Bezier GAN, which only outputs a Bezier curve. So it constrains the output to be Bezier curves. And for bicycles, again, training GANs can be tough. So we have a lot of tricks and knowledge which we impose. For example, we input the part information also. So we have information about individual parts of an assembly, and we combine that with the entire assemblies to improve the training.
And how much data is usually required to train a gun like that?
Depends on the problem. And for example, the bicycle just had 4,000, but for the airfoils, we augmented the data set to make it somewhere around 36,000 airfoil training data. But yeah, it depends on basically when you're capturing the performance, how complex is your physics-based simulator also, because you're trying to capture not only the shape, but also the underlying performance metrics. And the data set size depends on it.
And we have time for one more question for Mina. And how do you encode the dynamics of the movement in the robotic projects, the behavior and the joint constraints into a grammar?
I'm sorry, how do you encode the dynamics of what?
Of movement. So each robot has to move somehow, and the grammar itself was designed such that each robot can walk. So how is this encoded in the grammar?
So the grammar doesn't actually directly encode the dynamics. It makes sure that the parts that are connected to each other can work with each other. So it doesn't make sense to connect certain types of links together and certain types of joints together, and then have, for example, a leg composed of just links and no joints. That wouldn't be able to walk. So a construction that is composed of components that can work together and also be able to walk is what I meant by this constraint. So it doesn't immediately encode what is the dynamics going to be or what are the controllers going to be for that robot structure.
I see. Okay, thank you very much for your great talks and for staying for the Q&A session.